Hello everybody. Let us now discuss a few problems on electrical potential energy or electrostatic potential energy. So let's start with some examples. The first example. 2 point charges Q1 minus Q1 and Q2 negative and positive are initially kept at some separation, some distance r from each other. Find the amount of work done needed to double the separation between them. We need to pull them apart so as to increase the distance between them to 2r, and we have to find the work done in the process. Now we know that work done can be calculated by computing the change in internal energy. So initial energy of the system, we know the formula for energy, that is 1 by 4 pi epsilon naught Q1 Q2 by R. Here it will be minus Q1 Q2. So initial energy of the system is this one, U initial, U for potential energies, this is constant K, minus Q1 Q2, the product of two charges with their sign, by the separation between them. Then finally this distance between them becomes 2r, they are pulled apart. So in the final state the energy of the system is this U final, the same way. The only change is that r changes to 2r. Now work done is always given by final energy minus initial energy. So work done on the system means work done by the external agent. This is the formula. Work done by external agent, final energy minus initial. We have the values of final energy in equation 2, initial in equation 1. Substitute the values. The final energy minus initial. Now it's a simple calculation. You would have the result. And this is the result. It was a quite simple question. Based on this formula, work done by external agent is final energy minus initial one. Let's see another example. Now here there are two particles of charges plus Q1, Q2. Both are positive charges. And they are released from each, released when the separation between them is r. If they are released, they repel each other. Distance between them increases and also the speed increases. Now you have to find the speed of each particle when the separation between them becomes 2r. Now here it must be mentioned that the two particles are having equal masses. So it's worth noting. The two particles, charges, they are having equal masses, m each. It should be mentioned in the question. Anyhow, let's see. Now one thing is very clear, that no external agent is involved over here. You are just leaving the system on its own, releasing the system. So as there is no external agent involved, total energy must be conserved. In this situation there is no external force involved, so the total energy of the system remains conserved. Let's write down the initial energy of the system. U initial or UI. It's K 1 by 4 pi epsilon Q1 Q2 by R. And the kinetic energy initially they were released from rest, means initial kinetic energy is 0. And in the final state, separation between them becomes 2r. This r becomes 2r. So this final potential energy will be this K Q1 Q2 by 2r. And then final kinetic energy. Now as I told you, both are having equal masses. As they do have equal masses, both will have equal speed. We'll have to add up the kinetic energy of both the particles of the system. So final kinetic energy is half mv square for the one of the particles and this for the other. The sum is mv square. So this is the total final energy. Now by conservation of energy, initial potential energy plus kinetic energy is this final potential energy plus final kinetic energy. This way, initial potential energy plus kinetic is final potential energy plus final. Put the values. This is the value of initial potential energy from here, initial kinetic energy here, final potential energy from here, final kinetic energy from here. Solve it to get the value of V. Just the half has been taken to this side, subtracted. Okay, that's fine. This is the result. See the calculation yourself. So this was the second question based on conservation of energy. Let's see yet another example. Now here in this system, there are three particles, each of having charge Q, and they are placed on the three vertices of an equilateral triangle, side A, B and C. And you have to find the net potential energy stored in the system, and also find the work done required to reduce the separation between the particles to half its initial value. Means we want to bring them closer so that the separation between any two particles becomes A by 2. Anyhow, the initial energy of the system, this comprises, there are three pairs of particles, this AB one pair, AC other pair, BC other pair. So there are three pairs, and hence there will be three terms of energy. So net energy is energy of AB, interaction energy of AB, BC, CA, three pairs. Now AB and BA, we don't need to take BA, it's the same thing. Just put the value AB, these two, forget about this one right now, these two, that is 1 by 4 pi epsilon Q into Q square by this distance A. These two are also the same. Now add this is simply 3 times this one. So this is the answer of first part. Now if we bring them closer so that the side of this triangle becomes A by 2, the energy would have similar formula. The only difference is that this A will be replaced by A by 2, and you'll have this as, this should have been A. It should be A. It's a printing mistake over here. Final energy, sorry, work done by external agent. This is final energy minus initial. Values of final and initial. This is the final one. Now here the printing mistake has been corrected over here. So here this term and this term, it should be have been A. So take care of these two. Anyhow, here it's okay, and we have the answer. We could see still another example. Now in this example there are four particles, each of charge Q and located at the four vertices of a square having side A. We have to find the net potential energy of the system. Again we'll proceed in the same way. We'll just check out how many pairs are there. There are 6 pairs, AB, AC, AD, pairing with A, with B, BC, BD, that with C, CD. So there are this net energies, these 6 terms. Out of these 6 terms, you can note that there are a few terms which have the same value. This AB, AD, CD and BC. between A and B, the energy is K means 1 by 4 pi epsilon naught Q square by A. Distance between them. Between AD, the same. BC, the same. CD, the same. So these four are same. And these two, just see AC, distance between these two, A and C. This is A root 2. So these two becomes equal. So this is what you have. AB equal to AC, AD equal to BC equal to CD, and this is 1 by 4 pi epsilon naught Q square by A. Similarly, these two, AC and BD are equal. The same formula, just the distance between them becomes root 2A. This way. The final energy or the net energy is the sum of these two. 4 times this one plus 2 times this one. So this is the expression for final energy. Let's see still another example. Now this one. There's a uniform ring having radius r, this ring, and charge q is distributed uniformly on its circumference, and this ring is held stationary. There is another particle of charge minus q kept at point A. Its mass is m. This is released from here so that it moves downward. As it comes downward, its speed increases. We are supposed to find the speed of this particle when it reaches point O. So here, even the system is released from rest, energy is conserved. Anyhow, initial energy of A. This is very simple. The energy of a charged particle in a field is the charge multiplied with potential of that point. So energy of this particle over here is its charge multiplied with potential of A. Potential of point A due to all these charges. A ring, its K means 1 by 4 pi epsilon naught Q by under root x square plus r square. This minus Q, this is the potential at A. This is energy, initial energy, energy at A. And kinetic energy at A is 0. This particle comes over here. When it reaches over here, the potential energy at O, the same formula, minus Q into potential of O. Potential of O due to this ring is simply KQ by R. So this becomes minus Q into potential at O. It should be Q square. Q square. Now, this term should be Q square. Anyhow, further, kinetic energy at this point O will be half mv square. We are assuming this speed to be v over this point. Now apply this formula, conservation of energy. Potential energy at O plus kinetic energy at O is in potential energy at A plus kinetic energy at A. Substitute the values this way. Now we can calculate V. It's a simple calculation. That's all.